Namaste, this is MSc second semester class of physical chemistry, and today we discuss here about the Schrodinger equation. This equation is an 8 values wave value equation for the energy of or Hamiltonian operator. Its wave values provide the only allowed energy levels of the system. First is time dependent equation. If the Hamiltonian operator contains the time variable explicitly, one must solve the time dependent Schrodinger equation. Before moving deeper into understanding what quantum mechanics means, it is useful to learn how the wave functions psi are found by applying the basic equation of quantum mechanics. The Schrodinger equation to a few exactly soluble model problems. Knowing the solutions of these easy yet chemically very relevant models will then facilitate learning more of the detail about the structure of quantum mechanics. The Schrodinger equation is a different equation depending on time and on all the spatial coordinates necessary to describe the system at hand. 39 for the H2 example cited above, it is usually written as H psi is equals to IH del psi upon del T, where psi t is the unknown wave function and H is the operator corresponding to the total energy of the system. This operator is called the Hamiltonian and is formed as stated above by first writing down the classical mechanical expression for the total energy in Cartesian coordinates, the momenta and then replacing all classical momenta pj by their quantum mechanical operators. Pj is equal to minus ih del upon del q. For the H2 example used above, the classical mechanical energy of all 13 particles is written by this equation 1.44, where the indices I and j are used to label the 10 electrons whose 30 Cartesian coordinates are q, I and a and b. Label the 3 nuclei whose charges are denoted z and whose 9 Cartesian coordinates are qa. The electron and nuclear masses are denoted me and ma respectively. The coordinating Hamiltonian operator is given by this equation 1.45. Notice that H is a second order differential operator in the space of the 39 Cartesian coordinates that describe the positions of the 10 electrons and 3 nuclei. It is a second order operator because the momenta appear in the kinetic energy as pj square and pa square, and the quantum mechanical operator for each momentum p is equal to I minus ih del upon del q for the first order. The Schrodinger equation for the H2 example at hand then reads by this equation 1.46. The Hamiltonian in this case contains T. Now, an example of a case where H does contain T occurs when an oscillating electric field echoes along the x-axis interact with the electrons and nuclei and atom. This equation is added to the Hamiltonian, where here x and xj denote the x coordinates of the its nucleus and the j electron respectively. Now we discuss here about the time independent equation. If the Hamiltonian operator does not contain the time variable explicitly, one can solve the time independent Schrodinger equation. In case where the classical energy and hence the quantum Hamiltonian do not contain terms that are explicitly time dependent, the separations of variables techniques can be used to reduce the Schrodinger equation to a time independent equation. In such cases, H is not explicitly time dependent, so one can assume that psi is one of the form psi qj t is equals to psi q1 f t. Substituting this and stars into the time dependent Schrodinger equation gives by this equation 1.49 dividing by psi qj f t then gives by this equation 1.50. Since ft is only a function of time t and psi qj is only a function of the spatial coordinates, and because the left hand and right hand sides must be equal for all values of t and of qj, both the left and right hand sides must equal the constant. This constant is called E. The two equations that are embodied in this separation Schrodinger equation read as follows. So this is about Schrodinger wave equation. So in summary, whenever the Hamiltonian does not depend on time explicitly, one can solve the time independent Schrodinger equation first and then obtain the time dependence as exponential minus I et upon h once the energy is known. In the case of molecular structure theory, it is quite daunting task given to approximately solve the full Schrodinger equation, because it is a partial differential equation depending on all the coordinates of the electrons and nuclei in the molecule. For this reason, there are various approximations that one usually implements when attempting to study molecular structure using quantum mechanics. Thank you so much.